first, some conceptual questions.
Yeah.
All right. Anybody ever been to somebody's house? A lot of times, like this happens in older houses, not like real old houses, but like houses that were built in the 70s. Anybody ever seen a door that has the door handle like right here?
Yeah.
Why? So what? Why? Well, that's a good question, right?
Yeah,
One of my parents' neighbors has their door handle like right in the middle like that, and like they've lived there like ever since we were kids, you know. And I always just thought it was weird, like this is so weird, right? But why isn't that a good place to put the door handle?
Because the distance is closer to the finish.
Right. If we look at our formula for torque, right, tau is equal to force times distance times sine of theta, right? Okay, sine of theta. If we put the door handle in the middle of the door, what are we doing to D? Decreasing it. You pretty much cut it in half, right? And as far as torque is concerned, that results in less torque, right? Which is what we need to open this door, right? We're trying to cause a change in the rotational motion, right? Good, Lauren.
So wouldn't you need more force then?
You would need more force to accomplish the same thing, right? So you find that if you, so Lauren, just, we've all done this before, right? But you come to one of those doors that, like, the ones that are right down there by the library, the ones that go outside, and they have the push handle on, right? And you hit the wrong side of it, right? So, Don, you've been there. Don's been in that boat before. I'm glad you showed up for this part, Don. So, anyway, so you hit the wrong side of it, right? But you don't want to look like a fool, so what do? Right? Can you still open the door from that side?
Yeah.
Yeah, you just got to do what?
Push harder.
You just got to push a lot harder, right? Because when you have that door that has the handle on it, the one that's the push handle, if you hit it on the wrong side, you've made D a lot smaller because you're applying the force very close to the point of rotation, the hinges. So in order to make up for that torque, what do you got to do force-wise? A lot more force. Good there? Questions? Okay. Say again? Yeah, they are. Yeah, especially if you're like in a big, if you're like in a, it's sometimes really hard to tell. So.
Any doors that have it looks like you have to pull.
But it's just really, it's got like a pull handle.
It's a handle that you
push. Yes.
Why?
Like, but where is that handle always though?
On the wrong side.
Well, it's never on the side by the hinges, right? It's always on the side opposite. So you have that long lever arm. So. All right. Let's. Come on. We're almost there. 15 minutes. Stay strong. Come on. Do it. All right. Number 8. Number 8 says, lifting a heavy item in an improper fashion, bending at the waist instead of bending at the knees, can result in back pain. Use the concept of torque to explain why back injuries occur. Anybody ever do this before? Have you ever hurt your back before? Just do it this way, like lifting something the wrong way? All right. So let's talk about this guy right here who looks to be in severe pain. So, all right, should have been his knees. Yeah, you can even see. You can't see it so good here, but he's actually even saying ouch. So, all right.
Is it his lumbar?
Oh, it's definitely lumbar. He's in the lumbar region right there.
He's like,
So, here we go. Okay. This right here, man. Let's go with a different color. Let's go here. No, I don't want arrows. Here. Okay. This is our rotating object, right? The top half of this guy. Because when you bend at your waist, you're rotating, right? Okay. And this right here, your hip, basically, and maybe a little bit higher up. That's your point of rotation. That's where we're spinning around, right? Right here, this part stays still, and then we bend around the waist like that, okay? So, in order to get the top half of your body to spin, you have to apply a force somewhere along the way, okay? Your back muscles, which are the ones that you're using when you bend at your waist and bend back up, are actually attached like here-ish, right? Because that's attached to your spine, like right there. Okay. This is D. That's your lever arm. How long is your lever arm right there? Not very far at all, okay? Which means, what do your back muscles really have to do? They have to use a lot of force, especially because here, and we'll talk more about this starting tomorrow, but this big package, right, is applying a force to you like this. Does that make sense? Lauren? Is that okay? You just made that funny face. That big package like that is applying a torque to you in the other direction. Okay? So here, right, but what about this D? It's a lot longer, right? So the torque of this box can be a lot greater than the torque of your back muscles because it has a much longer lever arm. Okay? So to overcome that short lever arm versus long lever arm, right? How much force do your back muscles have to apply? A lot of force, right? And a lot of times that results in ouch. Okay there? So, one more example. So, good.
Are we done?
Are you telling me or you done
Could
with
I
this?
have a question?
Okay.
No questions about like starting with the knees.
Okay. Well, actually, the question is more about using concept of torque to explain why back injuries occur. Right? So, when you bend at your waist, right, or when you bend at your waist instead of bending like this, okay, your back muscles have to apply a very big force to get your body to rotate back upwards, right? Sometimes your body just can't handle it. Your back muscles can't apply that much force, and they either tear or rip or, in extreme cases, pull off of your bone, and that's not good. So you don't want that. So we good there?
Wait, so then so when you bend your knees, is it because there's a greater distance between your bend?
Well, when you bend your knees, actually, you're using different muscles. When you bend at your knees, you're using these muscles, okay, which are a lot stronger than these muscles. Okay, so that's why, and now you're not torquing, right? You're going straight up and down instead of spinning. Does that make sense? Yeah, but these muscles here are a lot stronger. Each use your strongest muscle, but your butt is your strongest muscle. So.
I gotta count.
Maybe pound for pound. That's true.
I'll give your top.
That's true.
Yeah, I saw this guy.
It's the same guy who drank 87 gallons of milk, Luke.
No.
And that wasn't that guy. So, okay. All right. So one more body thing. Come on. Stand by.
Look at that time check.
I do teach chemistry. Well, I've taught chemistry in the past. A lot of the chemistry stuff that's in there I use for physical science. So. Stand by. This will look good when you watch it again. So, good. Look, there's back pain. Bouncing hammer. Talk about that a little bit later. We can test more. Pictures of boy on platform. Oh, look, there's a carousel from the other day. Come on. I think it's H.
So this is
Yeah.
quick question.
Yeah.
So I was playing Star Wars yesterday, and the case is pouring out, right?
Yeah,
And
it
we were
was.
talking about the speeders on Endor.
Yeah.
You know how they just go forward so fast they never fall to the tangential speed is just so great that they just fall.
Wow.
Maybe.
Never thought, like they're in orbit, maybe. Maybe like a really low orbit.
Because they just constantly go forward.
Never thought about it that way. Never thought about it that way.
What is tangent?
When you stop, you just fall flat on your
Tangential speed again.
Come on.
It's like it's
What?
You're pretty tired.
E, F, G, writing X, one that's like a picture of an arm? Of your, oh, there it is. Equilibrium elbow. You know, like this one. It's got bones. It's got bones all over it. You know, like not Kate's pucks.
I don't think bones age.
This one's got a muscle on
You
it.
hate muscle.
Okay.
I still have
All right. So one more thing on your body, why it kind of sucks. So, all right. Here's your body, or sorry, it's not your whole body. Okay. Anyway, when your arm bends like this, right? That's a rotation. The bottom of your arm is rotating, okay? And the rotation point is your elbow. Okay? Now, what muscle makes your arm rotate like this? That one right there. That's your bicep, okay? That's the one in the front, okay? So, in order to curl your arm like this, make it rotate in this fashion. Hold on, wait. Yeah, you not getting rid of it.
Come on now.
You had to be that guy.
He started with
Thanks, good.
Have a great day.
Yeah.
Dad.
Start.
Start it. What are you doing?
I can't learn until the timer starts.
Come on. We should just kept going. We added 8 seconds before we got late. It's about 8 seconds.
I don't know why we did
That was by a special request.
Okay, special request.
Special request for 8 seconds. So, all right. Anyway, your arm rotation. Okay? Your bicep is the one that makes your arm curl up. Okay. The rotation point is your elbow. How far away is your bicep acting on your forearm from the rotation point? Not very far at all. Okay. The lever arm in this case is very small. Okay. Which means how much force does your bicep have to apply to your arm to make it rotate upwards? Kind of a lot. Okay. Your arm would be much more efficient and could lift a lot more weight if your bicep was attached where? To your wrist. Yeah, if your bicep was attached way out here, right? Your arm could do a lot more work. You'd lift a lot more weights, right? But that might look funny, and
We would have like big triangular arms.
yeah, you have like big triangular arms.
We wouldn't be able to like bend the middle.
But here, right, by attaching your bicep way out there, okay, look what happens to your lever arm. It's a lot longer. That can cause a lot more torque. It can cause a lot more rotation. But, once again, we get into inefficiencies of the design model and stuff like that. So,
But we can't design it for the body. It's already created.
well, it's true, right?
Can
But,
we?
like natural selection and
It's
stuff
Star
like that.
Wars.
Natural selection has gotten us to the point where this apparently is the most efficient design.
Sure.
Yes.
So we can talk about the tricep.
Tricep's basically the same thing, except it's actually even a little worse because your tricep comes around the back like this and attaches like here. So the lever arm's actually even shorter there. Okay? Because if you think about how much you can curl versus how much you can tricep extend.
It's easier to apply greater force. Isn't it more? It's 3 muscles as opposed to 2. And
They might be able to apply more force, but if
it's
you
more
think about
used too. When do you ever go like this?
anytime you lift anything to
Well, okay, yeah, but that's like,
I'm not talking about
yeah, I'm actually gaining a lot of muscle right now.
So, here, look. 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 I use this all day long. You're right. I mean, obviously.
Humans are the worst thing that happens to us.
What?
Humans are the worst thing that happens to us.
I mean, yeah, the words.
No.
So, like the ice age probably wasn't so high, you know. So.
But global like takeover is
This is a discussion for another class, I think. So.